By watching this video, I want you to be able to analyze transformations of functions. In general, a parent function is the simplest form in a set of functions that form a family. A parent function is that function with which we compare all other functions to. Each function in the family is just a transformation of that parent. The types of transformations that we look at, you've looked at before in Algebra 1, in geometry. We're just going to kind of review them in this, and then we'll see them occur throughout the rest of the course. One type of transformation is a translation. A translation shifts the graph of a parent function horizontally, vertically, or both without changing its size, shape, or orientation. For a positive constant k and a parent function of f of x is equal to, or f of x plus or minus k is a vertical translation. For a positive constant h, f of x plus h is a horizontal. So in other words, k is going to be outside of the initial function, meaning it changes the entire initial function by moving it up or down, and the change that is horizontal will be inside the function. It will be included. It's a change on x rather than f of x, which is our y value. Okay? So keeping that in mind, if we have a vertical translation, we want to say how are the functions y equals x and y equals x minus 4 related. If we just have y equals x, that function I can do in black. It would start at 0, 0 because its y-intercept would be 0. And because this is 1x, it would have a slope of 1. So that means it goes up 1 over 1 every time. That would be this line right there. Okay, so this is y equals x. If we translate that, we would have y equals x minus 4. Then to make a table of that, we could do it in two parts actually. We could say x, y, and for the first one at -2, -1, 0, 1, and 2. I'm just picking 2 points to the right of the origin, 2 points to the left. Every value of x will be the same for y, so we'll say -2, -1, 0, 1, and 2. But when we translate this, when we tack on that -4, what I'm going to do is say this same table, I'll use the same inputs, but now my output's going to change. I'll use the -2, -1, 0, 1, and 2. But this time when I plug it in, I'm going to have -2, which was my original, minus 4. Now I'd have -6. I'd have -1 minus 4, which would give me -5. 0 minus 4, -4. 1 minus 4 would be -3. And 2 minus 4 would give me -2. So my new coordinate points are going to be -2, -6, -1, -5, 0, -4, 1, -3, and 2, -2. Notice that what happened actually is my x values stayed the same, but all of my y values changed. That's because it's a vertical translation. It moves the y values. Okay, so we're going to go ahead and plot these points. So at -2, we're at -6. At -1, -5, 4, 3, 2. Now this line, I'll try to draw it through there. Okay, if I could draw it a little bit straighter, you would see that it is parallel to that line. it is this exact line moved down 4 units. Every point is the same, only down 1, 2, 3, 4 units. Okay, so how are the graphs related? Well, y equals x minus 4 is a translation four units down of y equals x. So they're the same graph, it's just been translated 4 units down. Okay. Let's take a look at example 2. It says, what is the graph of y equals x squared translated up 3 units? Okay, let's start with the table this time since it's not a line. I know it's not a line because of that squared. So I'm going to say y or x equal, x and y for my table over here. I'm going to plug in my x values, so I'm going to use that -2, -1, 0, 1, and 2. Those are almost always the coordinates I choose. If I plug in -2, I'm going to get -2 squared, which would be +4. If I plug in -1, -1 squared is going to be +1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So that means my original function here has a point at 0, 0. It has a point at negative and +1, 1. And at -2, 4. As well as +2, 4. This would be a u, a parabola, parabolic function. Okay. This is our original, and please pardon, I know my drawing's not perfect there, but this would be y is equal to x squared. Now what we want to do is see what happens when we translate it translate it up 3 right. Okay, so this would change my x value. So what's going to happen is I'm going to have x, I'm going to put my middle table, and then I'm going to put my y value over here. Rather than changing our y value this time, what's happening is we're going to have x, and when we move it right 3, x always has an inverse effect, so we're going to say -3 squared. Okay, that's what this is going to look like. So the change on x always goes inside, and I'm getting that from, I guess it's on the other page. But if you look here when it says x plus h minus h, the sign has to be opposite for x. So to move it to the right, if you see the green, it was -h. To move it to the left, it would be +h. That's exactly what I'm doing here. I'm saying if we're moving it up to the right, then that means that my sign has to be negative to be the opposite. Okay, so here's what we're going to do. We're going to use the same values, -2, -1, 0, 1, and 2. We're just going to plug these values in. So this I'm going to say -2 minus 3 squared. -2 minus 3 would be -5, squared would be 25. -1 minus 3 would be squared. Would be -4 squared, which would be 16. 0 minus 3 squared would be -3 squared, or 9. At 1, we would have 1 minus 3 squared, which would be -2 squared, or 4. At 2, we would have 2 minus 3, which would be -1 squared, which would be 1. Okay, so just, I know some of these, how many of them are off the graph, but what I'm going to look at here is I'm going to say each of these points should be just moved 3 units to the right, right? So we're going to kind of see how closely these are. So at 0, we would be at 9, which is off our graph. Our negatives are way off our graph. Our positive value 1 would be at 4. Our positive value 2 would be at 1. And judging by this, if you look, this is 1, 2, 3 units to the right of that, 1, 2, 3 units to the right of that. If I just took this 1, 2, 3 units and took this 1, 2, 3 units, you would see that it really is that image just moved 3 units to the right. Okay, so we would be looking at the same parabola, only moved 3 units to the right. So this would be y is equal to x minus 3 squared. And we knew that that'd be a horizontal translation. That's what we were doing in the beginning. But notice how different our points came out to be. Even though we were using the same points, the parabola gets exponentially larger faster. And so that's why our points were so far off our graph for the negatives here. If we had kept going and did 3, we would have seen that 3 gave us 0. We would have had exactly that point. But it's just a movement of the graph. The translation just moves the graph up and down, left or right. On the other hand, a reflection is a different kind of transformation. It flips the graph of the function across a line, such as the x-axis or y-axis. Each point on the graph of a reflected function is the same distance from the line of reflection as its corresponding point on the graph of the original function. For a function f of x, the reflection in the y-axis is f of negative x, and a reflection in the x-axis is negative f of x. We're probably going to see much more, or many more examples of this negative f of x. That would be a reflection about the line x, or the x-axis there. This one would be more of a reflection side to side across the y. You do or have done both in geometry. Probably this one occurs more frequently. I'm not saying we won't use this one, but again, this one does occur more frequently. When we are talking about reflecting, this is let g of x be the reflection of f of x equals negative or 2x minus 1 in the y-axis. What is the function rule for g of x? So we come up here and look at this for a minute. It says in the y-axis. That means we're using this one. The reflection in the y-axis gives us f of negative x. That's what the reflection is. So what that means is everywhere we had a positive x, we make it negative. So we're going to say 2 negative x instead of positive x minus 1. So from that, we're going to say 2 times negative x would be negative 2x minus 1. That would be our value then of g of x. That's our brand new function. We took this old function f that we had here. We changed our x to make it negative so that it would be a reflection about the y-axis. And then we ended with our brand new function g of x, which is that one right there. Okay? If we were to graph these side by side, which I wish I would have put a graph here, if we would have graphed them side by side, we would see that this is a reflection of that across the y-axis. Okay? This graph was an increasing slope. This graph has a decreasing slope. Their y-intercept didn't change. We didn't move it up or down. We just changed its direction that it was headed. Okay. A vertical stretch multiplies all the y values of a function by the same factor greater than 1. A vertical compression, on the other hand, reduces all the y values of a function by the same factor between 0 and 1. For a function f of x and a constant a, y equals a times f of x is a vertical stretch when a is greater than 1, a vertical compression when a is between 0 and 1. basically this is saying that if you have a whole number that's greater than 1, or even a fraction, I guess, that's greater than 1, as long as the number is bigger than 1 inherently, it's going to be a stretch. If the number is between 0 and 1, any fraction, that means it's going to be a compression, a shrink or a compression. Okay, this could apply to positives and negatives. I think it may even be better when we're looking at this to say if the absolute value of A is greater than 1, meaning if that number is, say, -3, it's still a stretch. It's just a stretch and a reflection. If A is a number that is between 0 and 1, it doesn't matter positive or negative, because we just looked at the negative means a reflection, but the A value causes the stretch or shrink, okay? Or the stretch or compression. So in example 4 here, it says the table to the right represents the function f of x. What are the corresponding values of g of x and the possible graphs of, or for the transformation g of x equals 1/2 f of x? So looking at this, we have our table. So these are our table values. And we want to know the possible graphs for the transformation half of f of x. Considering what we just talked about, 1/2 would be a compression. So 1/2 causes a compression. Sometimes you'll hear that referred to as a shrink. So I'll put /shrink. When you have a compression, this is a vertical compression, it's going to change all of my y values, my output values, by 1/2. So what I'll do actually is I'll take all of our current values and I'm just going to multiply them by 1/2 every time. That's going to give me my new f of x, my new output value. Okay, so half of -6 would be -3. Half of -2 would be -1. Half of +2 would be 1. Sorry. Half of -4 would be -2. Half of 8 would be 4. Okay, so that would give us our outputs, or our new outputs. Our old outputs, I'll do in blue on the graph, we would have -2, -6. We would have -1, -2, 0, 2, 1, -4, and 2, 8, which is off our graph a little bit. But this function must look something like that. Okay. This would be our f of x. What's going to happen here with our compression is that each of those are cut in half. So at -2, we're actually going to be at -3. At -1, we're going to be at -1. At 0, we're going to be at 1. At 1, we're going to be at -2. And at 2, we're going to be at 4. I'll put that on the wrong line. At 2, we're going to be at 4. So 2, 4. Okay, so if we follow this along, it's going to have that same shape. But notice that everything kind of got smaller. It's hard for me to draw on this real clearly, but everything did compress. It got smaller. It shrank down a little bit. That's what that 1/2 caused to happen. If it had been 2, what would have happened, inversely, is that everything would have stretched out a little bit. So we would have had a stretch on this, and it would have been skinnier looking, maybe more so than a little bit wider looking. Okay, to summarize transformations of functions, we have vertical translations that move the graph up or down, horizontal translations that move the graph left or right, and we say that right is always negative, left is always positive, the number with x is opposite. Okay, the vertical compression that transformed the graph to be a stretch would be when a is greater than 1, a compression when a is a fraction between 0 and 1, and the reflections, of course, if it's negative of f of x, it's going to be a reflection on the x-axis. If it's a reflection by the y-axis, we're going to have f of negative x. A couple more examples here. If the graph of g of x is the graph of f of x equals 3x stretched vertically by a factor of 2 and then reflected on the x-axis, what is a function rule for g? Okay, here's what we're looking at. We're starting with f of x. That's our original function. What we want to do to that then is stretch it. So we're going to stretch by a factor of 2. That means 2 times our value of f of x. And then we want to reflect it on the x-axis. That would make all of our y values become opposite signs. So we would say negative 2f of x. Okay, this is our end goal. That's what we're trying to do. So to write a function rule for g of x, we have to take f of x, which is that 3x, and do each of these things to it. So I'm going to say g of x is equal to, this is my end game, so I'm going to say negative 2. My value of f of x is actually 3x, so I'm just going to substitute f of x with 3x right there. And then g of x would be equal to that product, which would be negative 6x. That would be our value of g of x. So negative 6x would meet the requirements of being a vertical stretch of f of x and a reflection about the x-axis. That would be our rule. Okay, for part B, it says, what series of transformations changes the graph of f of x to the graph of g of x, given the 2? Okay, so what we want to do kind of here is work backwards. We want to look at f of x and say, what did I have to do to it to get to g of x? So for starters, you notice that in this one we have x squared, or 3x squared, and this one we just have x squared. Somehow they had to take 1/3 of that, right? So somehow they had to take 1/3 of f of x to get to g of x. But then we have a, instead of a +4, we have a -1. Well, if we started with +4 and ended with a -1, then they had to subtract from that 5, right? They had to subtract from the original f of x 5 units. So what series of transformations did it undergo? Well, it's a vertical compression because of the 1/3. And then it's a translation five units down. I hope that watching this video helps you out. Thanks.